So, hello everybody. My name is Graciela Gelmini, and I'm originally from Argentina, actually. That's why my Gelmini is because of my Italian ancestry, my grandparents, but actually my mother tongue is Spanish. In any event, I prefer that you ask questions whenever you have them. There are no silly questions. There may be silly answers, but in any case, there are no silly questions. So I'm not going to make interruptions or pauses for your and ask for your questions because then I forget. I forget to do it because I get too much interested in whatever I'm saying. But I look at you, so you just raise your hand and then we discuss whatever it is at the moment. This is best. And of course, if you have questions later on, uh, two. I mean, there's no. Okay. And I want to say that it's amazing how each group gets its own characteristics. And if there are a few people who ask questions, then everybody else starts asking questions. And this is the best thing, because the worst for a lecturer is have no response. I don't know what's going on. I don't know if it is too easy, too difficult, if I'm missing you entirely or if you are bored. You have to be interactive. And so I look at you and I see, but in any case, if you ask me, I will realize if I have to, how I shape my future lectures, which I haven't entirely finished yet, will depend on this. Okay, so let us start. So the search for the dark matter, actually, this is the most abundant form of matter in the universe, is multi-pronged. It involves cosmology, as you saw today. Searches are colliders, indirect detection and direct detection. We are going to concentrate on direct detection today. So this is my outline, potential outline of my talks. I will start today with a brief introduction to the observational evidence for dark matter, namely what is that we are looking for. And some of the candidates, you will see that will give you some information that will be recurrent later on. And then I will go through an introduction to dark matter detection, and I don't know how far I will go afterwards. So my intention is to start with non-directional direct detection of WIMPs. I will explain the difference between WIMPs and light dark matter in a moment. And then really towards the end, the last lecture, which will be Friday, then address direct detection of light dark matter, although the difference between WIMPs and different types of dark matter will be done today. Okay, so a brief review of our universe, just to say what we know about the universe. So we live in a galaxy. Galaxies are the building blocks of the universe. This is the Milky Way. Well, it's an artist's rendition of the Milky Way, which is the bar galaxy. The position of the sun is about 2/3 from the center, is 8 kiloparsecs. And this is the Sagittarius dwarf galaxy, the nearest dwarf galaxy. It would be really very prominent in the night sky if it wouldn't be because it is behind the center of the galaxy, and we cannot observe light, visible light, passing through the center of the galaxy or from the center of the galaxy, so it's obscured. But actually, the Milky Way is absorbing, is destroying the Sagittarius dwarf galaxies, and I will mention these trailing and leading trails. The Sagittarius galaxy has gone around the Milky Way several times, being destroyed in the process. Now, this is just the neighborhood of the Milky Way. This is the Sagittarius star, and there are the Sagittarius dwarf galaxy, but there are many other galaxies that are satellites. The most important, dynamically speaking, is the Large Magellanic Cloud. Actually, the Large and the Small Magellanic Clouds you can see actually by eye, the naked eye. The rest, not so much. Now we know that, many, many more, about 60 or so have been discovered in the last 10 years. Many. We are in a local group of galaxies in which there are three very big ones. This is not so important for direct detection at this point. In any case, and all of them have different dwarf galaxies. There are some that are bound actually to the local group and not to any of the big galaxies. Moving ahead, actually, you can see that at the so we live like in the peripheria of a cluster. A cluster has hundreds of galaxies. The nearest is the Virgo cluster, but there are many other clusters. And you see that at the level of superclusters, the structure is better defined by filaments and walls and voids and so on. So why I mentioned all of these different structures, because they are all dominated by dark matter from dwarf galaxies onwards, actually are dominated by dark matter. And we have evidence for dark matter in many, many different scales, and in particular, something that will be very important for us is the rotation curves of galaxies like ours. So the problem of the dark matter has been with us now since the 30s. Probably this guy, Fritz Zwicky, was not the first, but one of the first. And actually here you can see cold dark matter. Of course, dark matter is a misnomer. It shouldn't be dark. This is dark because it absorbs light. Light should be invisible. But in any case, we have already long ago lost our right to rename this matter. In any case, so he studied actually with the virial system, the virial theorem. He studied the clusters of galaxies. With this type of measurements and also gravitational lensing, we now know that actually that there is almost 6 times as much matter than the visible matter. Visible is what you can assign to, light and gas and dust and so on. Now, in the 1930s, this was not really recognized as a serious problem yet. It was in the 1970s with rotation curves that actually people saw that if most of the matter would finish where the light finishes, which would be approximately here, then we should have started to see a 1 over square root of the distance from the galaxy law in the rotational velocities of objects that are bound to the galaxy. And that is not what is observed. What is observed is that the characteristics, circular rotation or average rotation velocity around the galaxy is more or less flat, which indicates that the mass contained within these orbits grows with the radius. And so there is much more matter than what is seen, than what is observed, at least 4 times. Since there are 4 times, characteristically 4 times within galaxies, and there is 6 times in the clusters, and means that there is dark matter that is bound to clusters and not to galaxies. You know? And a little bit of this forms a tail, but very small, a tail of very high energy particles actually that we could detect if we are ever so lucky as to detect dark matter in direct detection. Okay. But it's small. All right. So the actual Milky Way is something like this. 85% of the mass, maybe 85% of the mass of the whole structure is in a dark halo, and the visible part is only a little bit in the middle. This is, of course, an artist's rendition, but a more, a better more scientific way of measuring this is with the rotation curves of our own galaxy. This is data for our own galaxy. It's much more difficult actually to see because we are within the galaxy. It's much more difficult to see the rotation curve. And so there is dispersion, but at the location of the sun, which is about 8.2, here is 8.277, Um, you can see it's about 230 or so kilometers per second, but there is a dispersion. This has been measured in different ways and with different data. Um, all this data I'm showing are after the Gaia mission. Gaia has been, if you don't know, an ESA, European agency mission, enormously successful, that actually has changed the way in which we understand the galaxy. It functions, it was launched in December 2023 and it was decommissioned in March 2025 this year. And so data from the data release number 3 has been used here in all of this, either by itself or together with other different data and so on and so forth. There is also the collaboration gravity that has helped all of this, because there was a large uncertainty in actually the distance of the sun from the center of the galaxy, and it has been measured actually much better than ever before with this mission. In the first results came in 2018. So here you see again, this is the data that these people prefer, but actually there is a large dispersion of the data. This is another study using the same type of data with different techniques and so on. So you see that actually, even with all of this, there is a certain dispersion. This is where the sun is, and I would say about 230, but plus minus something. In any case,
the error bars, the outskirts gets larger because we have less objects that we can use to...
Yeah, because it's more difficult, I think, to study. I'm not an expert in this, but in all of them, and moreover, you can see what they call it the Keplerian descent. I mean, a 1/square root of the radius onset at some point, because we don't know exactly where the halo of our galaxy finishes. It will finish where we see the 1/square root of the law setting in, the Keplerian decrease. And so the people are very interested in modeling this part and so on, but it's very difficult, yes, as you can see. In any case, for direct detection, what is most important is near us, what happens near us. Okay, at the largest scales, we have to use general relativity or your preferred variation, but it has to be some a theory of gravity. And then several data at very large scale structure, the CMB, PMB spectrum, baryon acoustic oscillations, supernovae, type 1.8, and the large scale structure of the universe. And this is how we know that actually dark matter accounts for about 26% of the content of the universe, while our type of matter is less than 5%. So here it is, our type of matter is, actually there are several indications, it's about 5%. The total amount of matter is about 30%. And the rest, we believe, is dark energy of one form or the other. We'll see. So after 90 years, what is that defines the dark matter problem? And you will see that in the end, when I am done, we are going to get to the bottom of a page, and that would be it. But I'm going to go very fast. If anything that I say is not understandable, so please ask, and I'll explain more. I will go fast, as I said. First of all, is that it has attractive gravitational interactions. Dark matter behaves like normal matter, except that we cannot see it or detect it in any other way but gravity. That's the point. And of course, it has to be stable or stable enough because it is around. And so far, it has been observed only through gravity. So there is always this nagging idea. Maybe are we understanding wrongly gravity? Huh? And this nagging idea is going to persist. The issue is that you cannot test nagging ideas, is that you need a model that you can test and so on. And all the models that have been proposed fail in one way or the other because dark matter is needed in the early universe to explain the spectrum of the CMB, baryon acoustic oscillations in galaxies and so on. Now, before, it's a very complex problem. And these theories that are alternative theories of gravity with only visible matter don't work. Even this very complicated ether scalar tensor a few years ago, now it starts being understood. Of course, it takes some time to understand actually that these ideas work or don't work, right? It is not working. So again, dark matter is not observed to interact with light or with any other standard model particles, but that doesn't mean actually that it's entirely neutral or doesn't have any interaction. Hopefully not. That's why we are going to detect it. So it could have a very small electromagnetic coupling, such as an electric or a magnetic or an anapole. So a dipole or an anapole. Or it could be mini charge. Milli charge or mini charge is usually implemented through a mixing between a photon and a dark photon, or there could be many other small couplings called portals to other standard model particles, neutrinos, Higgs, of which gauge bosons. So these are magnetic and electric dipole moments. I think that you have seen this. Maybe you haven't seen anapole. Anapole is a relatively newcomer. Newcomer, in any case, 1958, but with respect to electromagnetism, sort of newcomer, understood. And so this is the type of coupling that you get. And actually, dark matter could have this, and it has been explored as possible, the dark matter candidates, possible couplings. Now, the way to implement a photon and dark photon coupling is through a term in the Lagrangian of this type. It's you knew for U1 symmetry, F mu nu is a singlet. And so F mu nu, electromagnetism in both cases, leads to the propagator of the photon. It's a kinetic term for the photon. Now, assume that you have across another U1 dark. It will have its own F mu nu dark, F mu nu dark. But then there's nothing that prevents, since these are both singlets of both U1, there is nothing that prevents to mix the two. And since this is a mixing in the kinetic terms, it's called kinetic mixing. Now, once you diagonalize your theory, you can see that actually the photon has a little component of the dark photon. And so particles that are coupled with full strength, a dark electron that has charge -1 of the dark, right, would appear to the photon to have epsilon -1. At this epsilon, that is the mixing. And so you will have milli-charge particles. And moreover, the dark photon, likewise, the dark photon contains a little bit epsilon of the photon, and therefore the dark photon couples to all other charged particles, usual charged particles, a little bit with epsilon. So it could be that these particles that are in dark charge could be analogs of protons, electrons forming hydrogens and maybe other atoms and so on. This has been proposed, atomic dark matter. And the hidden or dark photons could be themselves dark matter. For example, here under, it could be dark matter, but it would be very light dark matter. You see 10 to the -3 or below. It could be dark matter itself. And it has been searched for extensively and continues to be searched for. Or it could be a mediator, actually, for other particles, as I said. Okay. So the bulk of the dark matter must be nearly dissipationless. I showed you a moment ago that the halo is extended, the dark halo is extended, and the disk is in the middle. There has to be some difference between the visible matter and the dark matter that makes them end up in such different places. And the issue is that the visible matter is dissipational. What it doesn't mean dissipation, it loses energy. It loses energy, but it loses energy in an isotropic fashion, and therefore it doesn't lose angular momentum. So the proto-galaxy, whatever it starts with, a mixture of dark matter and visible matter, is supposed at the beginning to have a little torque. Why not? And everything rotates a bit. But then as the visible matter means atoms and molecules and so on, radiate photons, lose energy, and they fall in the potential well. As when they fall in the potential well, they lose, it's like in physics 1, when you do the exercise of the moment of inertia, you decrease the moment of inertia, and omega has to increase. So it starts rotating faster and faster, and finally there is an instability. Something that rotates fast enough is unstable towards the formation of the disk. Okay, so this is but of course, there is a few percent or more of the matter, the visible matter, that is in the galaxy, and that has not obstructed the formation of the disk and so on. So it could be maybe that this was proposed, and anyhow, that maybe a few percent or more could be dissipational. You see that now here we have already, I have said there are maybe dark photons, dark electrons, and so on. It's a dark sector. You see, it's not only dark matter particles, it's a whole sector of dark particles. And this would be, again, something. Maybe there could be a dark photon or something else that is light, and part of the dark matter is dissipational and part is not. That would lead in some corner of the, if it is dissipational enough, to have a double disk, a disk of dark matter besides a disk of visible matter. That would be great for direct detection, because you will have a spike actually of density at very low velocities or something like that. But Gaia, again, is all the Gaia results are compatible with having no dark disk. And actually, maybe it is a few percent of the local dark matter could be in a dark disk. No more. Although some simulations of structure formation show it that it is rare. It has to be through the merger that comes at the right angle and ends up being distributed in the right place. But with this type of dark matter, it would be pervasive. All galaxies would have a dark disk. That is not, doesn't seem to be the case. Okay. So, fifth, dark matter is mostly assumed to be collisionless. Most of dark matter is assumed to be not self-interacting, but the upper limit on self-interactions is actually huge. So the upper limit, here it is a barn per GeV. Barn, you know what the barn is, no? Barn is a big place where the animals are, actually. And this was, it seems to be, they were looking for, in Los Alamos, they were looking for a unit large enough for nuclear cross sections, and they were in the middle of whatever, and they saw barn, so they say, oh, why don't we call it a barn? So this is a barn, okay? That's this. A barn is a nuclear cross section, right? Is huge, and you see that here a barn. If you have a mass, the limit comes from mean-free paths, and mean-free paths depend actually on this ratio. And so what you put is a limit to this ratio, right? The GeV per barn per GeV. So if mass would be 100, whatever, it would be, the self-interaction could be 200 barns. Is huge, the upper limit. So we don't know if dark matter is self-interacting, but what we yes know is that even if they are very strongly self-interacting, they should be very feebly interacting with the standard model. The two things are not related. The two things. So there could be feebly interacting particles, FIPs, with the standard model. Okay. So here it is, the mass. Well, 70 orders of magnitude. The and the higher, and these are all proposed candidates, right? The biggest ones would be primordial black holes. The smallest one, fuzzy dark matter. I will mention both, but I will not later on talk about any of them. I would like to say fuzzy dark matter is a boson with a de Broglie wavelength, which is about 1 kiloparsec. So it's the Broglie wavelength, which is of the size of a small galaxy, or let's say we are at 8 kiloparsecs from the center of the galaxy. So it's a extremely large de Broglie wavelength. It may not be possible anymore to have this very big, but in any case, here you have going from smaller mass to largest, the ultralight bosons, axions, or ALPS, axion-like particles. And then we move maybe KV, particles, sterile neutrinos, light dark matter, and WIMPs. This is mostly what I'm going to talk about. But there are particles, could be elementary particles, could be even up to the Planck scale. Afterwards, they have to be some kind of composite dark matter, and so on and so forth. Now, let me mention that primordial black holes could be actually the candidates. You see that there is a range. This is called loosely the asteroid mass range, in which actually you could have the whole of the dark matter being in primordial black holes. Now, what are primordial black holes? Primordial black holes are black holes that are not astrophysical in origin. No? Very massive stars end up in producing black holes, etc. But they are produced in many different ways, but in the early universe. For example, in phase transitions, bubble collisions, whatever. There are many different ways, but they are all very early on in the history of the universe. In any case, I'm just going to mention. On the other side, there is this ultralight. They're called ultralight axion, ULAS, or scalar field dark matter, or wave dark matter, or fuzzy dark matter. All of these names are for the same thing. They are light bosons, very light. And in our galaxy, because our galaxy, I show you the characteristic velocity of the rotation curve, okay? This is what we see, the rotation, so the luminous objects, but actually anything that is in the same potential well should have the same characteristic energy. This is a virialized system. So 200, 300 kilometers per second is 10 to the minus 3. And so, and the density is about maybe, I will mention in a moment, about 0.4 per GeV per centimeter cube. So if you compute the Broglie wavelength of particles, and then you compute the occupation number, which would be simply the number of particles in a de Broglie wavelength cube volume. You can see here 10 to the 44 if the mass of the particle is 10 to the minus 9. The de Broglie wavelength is inversely proportional to the mass, and here you have the number density. We measure the density, but of course the number density will be the density divided by the mass. So there is a dependence as m1 over m to the fourth. So you can see when is the occupation number, namely how many of these particles are overlapped, right? Occupying the same wavelength, occupying the same wavelength. So in this case, it will be 10 to the 44, enormous number. You see that the number is about 1 for a mass which is 30 electron volts. When you get to very large occupation numbers, and then the fluctuations become much smaller, square root fluctuations are a square root of n, right? So when a square root of n becomes much smaller than n, then you have a description, a better description is a description as a classical field. And so this is why this is a scalar field, classical field, dark matter. Fuzzy means fluffy or smear out, and this refers to the effects of the uncertainty principle or quantum pressure that this uncertainty principle has, which forms interference patterns, big interference patterns that you can see in a structure formation with these things. And also it balances gravity to form dense and stable soliton cores. Actually, I must say that the first paper on this was a paper that I did with Remo Ruffini, actually, while I was visiting Rome. I was still a student and visiting Rome. And Baldeschi was a student of Ruffini. And we wrote this paper, actually, and it's not that bad, actually. We considered a halo formed by bosons. This is 1983, is the same year in which axions were proposed as dark matter candidates. In any case, I wanted to mention this. There are several limits. I'm not going to enter into this, but there are several limits on how light this the mass of this object, the fuzzy dark matter can be. And it seems this is not the subject of my talk, but it seems to be actually that you can get to 10 to the minus 16, not 10 to the minus 20. People say 10 to the minus 22 or so, but probably it can be as small as 10 to the minus 16. In any event, those are the extremes, and mostly, so this is wave dark matter. Wave dark matter is what you are going to cover next week. I wanted to make this distinction. Why wave dark matter is because the occupation number is huge, and you deal with this dark matter candidates as classical fields, actually. It's a better description than particles. In any case, I will deal with particle light, mostly here in this regime, up to maybe 100 TeVs or so. The part of WIMPs, a part of light dark matter, that I will explain the difference in a moment. Although there are particles that could be as large as the Planck scale, I'm not sure. Planck scale particles you could detect wind chime, for example, gravitational effects. Actually, you could try to detect. It's not exactly direct detection, but it's gravitational detection. If I have time, I will mention that. But mostly, I will refer here to. I will concentrate on this mass range. Well, usually you have problems actually to get any problems to make it stable, to describe it even, to have a field theory that will make sense. And also, mostly here already, even before, what you have is composite dark matter that can be different type of degrees of compositeness. And so. It's a problem that you don't have a good description, actually, of a particle physics. So there are no models for that. But instead, yes, if they are macroscopic objects to some extent that are composites of some one way or the other. But there are some models in which that say that there is nothing. The standard model describes all there is up to the Planck scale. And then dark matter also is at the Planck scale, for example. So this is a possibility. Direct detection, we don't like that much, that possibility, but okay. Yes. Ah, no, this is approximately, right? Should be approximate. This is 1 electron volt. Approximate. This is not that doesn't mean anything. No. Yeah, the temperature now is 10 to the minus 4 electron volts. No, it has nothing to do with it. It's about, even I could have made it there, actually. But of course, here the occupation number is about 1. There is, again, a fuzzy transition, right? To some extent, you can say that they are particles. To some extent, you can say that they are fields. At some point, the description becomes entirely as a field, right? Or better as a field. Yeah, thank you. Okay. The bulk of the dark matter is cold or warm. That doesn't matter much for us because we are going to see direct detection of this independently of what they are, how they are produced. Cold and warm refer to how, it refers to the momentum. Namely, if they are relativistic, if they are becoming non-relativistic or completely non-relativistic at the moment, galaxy dwarf galaxy core size structures are first encompassed by the horizon. So the horizon grows essentially a CT, 2 CT during the radiation domination. And so it encompasses larger and larger structures at some point when these inhomogeneities that are already imprinted in the universe by an early episode, probably inflation or so on, when they are encompassed by the horizon, then they can be processed, they can start feeling gravitational interactions and evolve. If they are relativistic at this moment, the inhomogeneity is erased. The particles escape because they move with the velocity of light. And we see dwarf galaxy cores. Well, we don't know if dwarf galaxy cores are the smallest structures, or actually there were smaller still. 10 to the minus 6 solar masses is more or less where the boundary is between one and the other. Are they mini halos, namely structured smaller than 10 to the minus 6 solar masses? Then probably it was cold, namely had been already non-relativistic much before the temperature of the universe was a keV. Okay, now why is it important that it's cold or warm? Because in both of them, even with the differences that I just mentioned, with both, the formation of a structure is bottom-up. Namely, you form smaller structures first, and then larger structures start evolving, and so on. So the smaller structures are incorporated within the bigger structures. They merge with them. This is a simulation. This is among the bigger simulations, actually. Millennium. This is dark matter only. There are two types of simulations of a structure formation, either dark matter only or with the addition of the effect of baryons, which are called usually hydrodynamical simulations. This is a dark matter only. But you can see here, these are structures like our galaxy, and you can see all these other structures within and outside. So these are all evolving together. They collide with each other, they merge, they are incorporated, and so on and so forth. Why is this important? Because we can expect that there is a lot of dark matter that is not entirely virialized in our galaxy. And in fact, Gaia has seen an enormous amount of different streams and so on. I will mention a few that actually might be the biggest one. The biggest stream is the one associated with the dwarf galaxy I mentioned at the beginning, the Sagittarius dwarf galaxy. And although the stream passes, the stream goes around and passes through the disk at a position that is a bit different than the position of the sun. It could be that the dark matter that was in this galaxy is passing through the sun, and then it could give us a stream to measure, right? So there are inhomogeneities and Gaia has seen, of course, it has seen the stars, a billion stars, few billion actually, more than a billion stars. Okay, there is no cold dark matter or warm dark matter in the standard model. We don't have candidates in the study. The only candidates we have that are part of the dark matter actually are the neutrinos, right? Active neutrinos, the 3 active neutrinos. But they are hot dark matter. We know that they are hot dark matter because of BBN. Big Bang nucleosynthesis requires neutrinos to be almost in equilibrium. And that means that they were in thermal equilibrium when the temperature of the universe is about an MeV. They have to be almost in equilibrium. And therefore, you can follow the history. They at the KV with the masses that they have, they are very light. They were, even if they might be non-relativistic now, but the issue is not now, is when the temperature of the universe was 1 keV. In any case, we don't have any candidates, and so we need candidates, requires beyond the standard model. The issue is what beyond the standard model physics? And here, the scope of dark matter model has changed since people realized that there was a problem and maybe we require new dark matter particles. At the beginning, in the 1980s, when people were starting to realize that there was this issue, all the candidates came as an afterthought in models that were proposed to solve problems inherent to the standard model. For example, the hierarchy problem, the electroweak hierarchy problem, or strong CP problem, or the mass of neutrinos. And the lightest one generated the models that the earliest models for weakly interacting massive particles, WIMPs, or QCD actions of the sterile neutrinos. In the 1990s, people were very aware that actually you needed to have dark matter candidates. And so it became mandatory that in every model that you had, particle model, you had to produce a good dark matter model with a good density to be the dark matter, etc. Now, since the 2000s, this has changed considerably. So the dark matter models, or dark sector more than dark matter, were proposed independently of solving any standard model problem. There were models done to fit dark matter hints, of which there were many already, in indirect and indirect detection, or predict novel signatures, and then experiments to detect them. So this led to all types of dark matter interactions, to dark sectors, through seeing not observed yet in experiments, not because they are very heavy, as it could be for WIMPs, but because they are very lightly coupled. Namely, the portals are very small. The couplings are very small. So they could be light, but they are very small. So the couplings are very small and they are not produced. And then they were classified according to possible experimental signatures that you could have. So this is an experimentally driven or phenomenologically driven. Okay, I will mention some of the particles that I will mention later, just to tell you the variety, and some of them I will mention later on. The first is WIMPs, weakly interacting massive particles. They have close to weak order. Close is loose, because of course they have to have weaker than weak, otherwise we would have seen them. So the models started with massive standard model neutrinos that were of course rejected. And then in all these models, starting in the 1980s with supersymmetry, the lightest particle carrying a particularly conserved quantum number. For example, in supersymmetries are parity, okay? Or there are many other little Higgs, technibariums, whatever. All the lightest particle carrying a particular conserved a number, and there are several of them of this type. This is then a good dark matter candidate. The production that you will hear in another lecture, but in any case, they reach thermal equilibrium in via annihilation of the dark matter into standard model interactions. They reach thermal equilibrium and then they freeze out. They stop when the annihilation rate stops. Or it could be also producing the decay of another WIMP. This is called the super WIMP scenario. Typical masses are GeV 200 TeV. This is what I'm going to start discussing first. FIMPs, feebly interacting massive particles, or frozen in massive particles. They are never in equilibrium. Their interactions are so small, they are produced a little bit, they are produced a little bit, they are produced a little bit, and then the production mechanism ceases to be effective, namely the rate becomes smaller than the expansion rate of the universe, and then what was produced, and that's it. That's the way in which you produce them. So, as I said, freeze-in. And they have an enormous variety of different masses, sub-electron volts to hundreds of TeVs. This is the mass range of light dark matter and WIMPs, but the couplings are enormously small, so they are not a good target for direct detection. SIMPs, strongly interactive massive particles. In the old version of these models, 1990s, it was honest, strongly interacting. Namely, they interacted through strong interactions through QCD. This was actually rejected soon after. They did not survive. And they were revived about 10 years ago as a strongly self-interacting. You remember self-interacting dark matter? But still, they are feebly coupled to the standard model. So they are FIPS. They are SIMPs, but they are FIPS, right? Okay, so there are different models. I'm not going to enter the models. They reach thermal equilibrium, but within the dark sector. And they freeze out, but also in the dark sector, 3 particles go into 2 dark particles. This is called cannibalism, by the way, because they eat their own. Essentially, 3 dark matter particles hang up and 1 disappears, or 4 to 2, and so on and so forth. Okay. A particular type of SIMP is called ELDER, elastically decoupling relic. And this has, in particular, a little bit larger interaction with the standard model because of the requirements of the way in which it is produced. These are typical light dark matter, 100 keVs to tens of MeVs. These are typical candidates. And then there are more PIMPs. Planckian interacting massive particles. Assume that new physics comes only at the Planck scales. This is a hidden sector connected effectively to the dark matter only through gravitational interactions or gravitational order interactions. In any case, the most typical is the Planck scale, and they interact gravitationally, very difficult. For usual direct detection doesn't work, but there are some ideas. For example, wind chime. If I don't have time to present it, you can look up this idea. In any case, there are these models, GIMPs, gravitational interacting massive particles, same thing, same type of models. And of course, there is more. I will not talk much about actions, instead to mention briefly that there are experiments to detect light dark matter via scattering that can also detect lighter particles via absorption, in which the whole mass is given, not only the kinetic energy. So these are axions and axion-like particles. I'm not going to mention much of them. The production is typically as a boson condensate or radiated from axion topological defects, could be strings or walls. And these are typically very light for the axion that is actually coupled to QCD, 10 to the minus 4 to 10 to the minus 10, and ALPS can be extremely model dependent. There is a name, WISP, weakly interacting slim particles, that actually is the combination of axions and axion-like particles and hidden photons. In order not to be all the time saying axions or ALPS or dark photons, then you say WISPs, essentially. This is spin 0 or spin 1 photon combined name for both. This German people did this because this thing of calling particles slim is very odd. In any case, the more, the odder, the better, because people remember, so maybe that's the point. So weakly interacting slim, slim is thin, not, a thin particle. In any case, okay. And then there are many others. Q balls, for example, non-topological solitons, sterile neutrinos, WIMP-SILAs, and so on. I'm not going to much mention some of them, but there are still mentioned. And this list is not even complete. But this is just a variety, right? A large enough variety. Okay. Now we start in earnest with searches. Please tell me about who is there a chair here? No. I can ask you because otherwise I will continue forever. Maybe 3 minutes, 2 minutes, 3:30, right? I have an answer. Okay. All right. Otherwise you tell me, if I'm, okay. So direct detection was proposed in the 80s, 1984, actually, proposed by Andrzej Drucker and Leo Stodolski in 1984, and followed by Goodman and Witten that did immediately after. And so Drucker and Stodolski, believe it or not, they were proposing small granules of superconducting granules, and actually superconductors are being used now. Now they are proposed actually in the form of wires, but it's curious how the ideas are recycled. And for a long time, this idea was not considered viable, but in any case, so superheated superconducting granules. In any case, so it looks for energy deposited within a detector through either scattering or absorption of dark matter particles in the dark halo of the Milky Way that are passing through the detector. And the characteristic velocity is very small, and so these particles are non-relativistic essentially. So the detectors are sensitive to very different energies. The traditional experiments with which I'm going to start started in the 1980s again onwards, have usually KVs of threshold, energy threshold, for scattering off a nuclei. So the kinetic energy is about 10 to the minus 6 of the mass. So the reach, if you have the kinetic energy being approximately keV, the reach is about GeV. These are WIMPs, these are the normal winds. Now they are in the multi-ton. These are LC, xenon, and ton, and then the dark side, and so on. Right. And then 10 to the minus 6 electron volt was for the QCD axions in resonant cavities. Those were the two types. And then in the last 20 years, there have been an explosion of different ideas, mostly in the last 20 years approximately, driven by impressive developments in detectors, in quantum sensors, etc. And so Elastic scattering. Yes, this is a wavy assumption. Yes, elastic scattering. Why? What do you have in mind?
No, because in principle, if I have an elastic process, I can release more.
In the elastic process, you have there are it's possible. You mean in elastic process in the nuclei? You need
Either in the nuclei or
in the dark matter itself doesn't help you that much really in elastic dark matter. It's still the the range is not so much. You see in any case we are going to return to that, but it's difficult to beat the coherence, right? Because in elastic scattering you have coherence. A square is a lot. It helps you quite a bit. You lose coherence usually when you, yeah. So it is suppressed and so on. So mostly they are built around the idea of elastic scattering. Okay, so there have been a scattering and absorption for energies above electron volt of electrons. This is what light dark matter it is, a scattering or absorbed of electrons essentially, or a scattering and absorption of even collective excitations or even smaller ones, allowing to reach even ultralight dark matter. That will be the subject of next week. People will talk about that. Okay, so what is that we are measuring? This is an old plot 20 years ago about, in which it showed some curve, some rotational curve. And this is what I showed today. This was an earlier version. And then you can see that if the density is 0.3 GeV per centimeter cube, this was a number that traditionally is used and was used before. It seems to me that it's a bit bigger, actually, 0.4, 0.445. I will show you in a moment. But in any case, with 0.3, then you have many, 10 to the 7 particles if you have the mass GeV, and otherwise it scales as 1 over MeV. So they are passing through us per centimeter square per second. And there is a dark matter wind due to the sun's motion around the galaxy. We don't expect the halo to have much of a angular speed. Could have a very small one. Usually you say that that is at rest. It's not about approximation, right? Because the disk is moving so much faster than the so the wind is this average velocity. We assume that dark matter is at rest. The bulk of the dark matter is at rest with respect to the galaxy, and we are receiving this at the wind with an average velocity due to sun's motion. So the velocity of the average velocity of this dark matter wind is minus the velocity of this Earth, actually, on Earth, minus the velocity of Earth with respect to the galaxy. Now, are there better measurements? As I said, yes. So here there are two types. So what is the local? So what is that we are trying to measure in data detection? What is the density, the local density of dark matter? Well, there are two ways of measuring. One is global methods that try to fit the rotation curves and use data of the whole structure of the halo and feel the whole structure of the halo, fit the whole structure of the halo to different type of measurements, and then they infer what is the local density. And local methods, so studying the motion of the stars, the vertical kinematics, and so on and so forth, the time-varying structures in the local phase space, and so forth. So this is from a paper 2024, and they mention several others, So in their paper, they concluded 0.42 GV per centimeter cube, but they showed the relatively recent 19, 20, 21, 24 different other studies of both types. And you see that the average is 0.39 and 0.41, close to 0.42. This is another study. This is 2023. Again, you can see various different measurements. And this band here is 0.47, plus minus 0.05. This is the conclusion of this paper in particular.
Can you measure growth without assuming any velocity dispersion, or you need to fit
Well,
a model altogether?
there are two ways of doing it. One is, I am not an expert. By no means, I'm a particle physicist. I'm not, no, but what I mean is that either you fit the speed, the whole, you model the whole halo, and then you infer the local properties. This is a way of doing it. A very large structure, data fitting the circular speed curve, anisotropies, galactic mass model, circular speed. Okay, all these global things. Or you try to infer from how things move in the vicinity of the sun. And they give, they're very different, but they give in last instance results that are not all dissimilar. But they have a spread. This is what, I mean, the spread, of course, is in the plus minus here, but visually, maybe it's better. We are visual people, right?
No, but what I'm saying is that in the end, what you are really measuring is acceleration, I suppose. So you are
Yes.
measuring the gravitational potential.
Yes, you're
So
measuring.
for that, you need to use Newton equation to go
Yeah.
to energy density.
Yes,
But
exactly.
then you need to assume something about the behavior of your stuff. So in the sense that
because you usually measure velocity, right? You rarely measure, like, you can infer.
Yeah, if you have enough tracers, you can infer the gravitational potential in which these tracers are moving. So the idea is, what is that you model? Do you model only these tracers in the neighborhood of the close to the sun? And close to the sun is big, even considering the whole thickness of the disk and so on and so forth, right? It's not very local. Or the whole galaxy. And these two methods are, you see, giving results with all the dispersion, of course, but they give results that are not all dissimilar. And they are around 0.4 or above 0.4, some of them. Yeah. So some people, yes. Sorry, can you say again? Local measurements are these. We don't have any other way of inferring what is the dark matter. Maybe at some point we are going to measure. All of these things are at enormous scales. There is nothing that will give you information of dark matter at the scale of the Earth or the solar system, as it would be if you measure it in the laboratory. There are no other ways of inferring but having enough tracers. You have to see all these stars. What are the tracers? The stars and stuff like that. They are moving, and they are moving in a potential well, right? Yes. So these are scales of tens of parsecs. That's how you can measure the dark matter. There is nothing, no simulations, no measurements that can tell you exactly what is the density here. They can tell you in a big volume around the sun, around the position of the sun, what should be. But if you want to actually measure what happens at very small scales, you have to actually find that in direct detection. There is no other way. Then you can measure actually the distribution, the velocity distribution, and so on and so forth. Now, of course, the density enters multiplying everything in the rate and so on. So it's a prefactor. So actually, there will be a degeneracy between the density and the cross-section, right? They both enter multiplying. But it also is true that if it is 0.4 or 0.5 or whatever, your cross-sections accordingly change also your limits. But in any case, it's a multiplicative factor. But what I mean is that many people adopt now 0.4 or 0.45 even, not 0.3. 0.3 is a sort of an outdated number. Okay. So for a while, I'm going to use the standard halo model. The standard halo model is the spherical cow, everybody knows yeah. So this is the spherical cow of halo models, essentially. But it's not that bad. Actually, as a bulk, it's not that bad. Is modeled as an isothermal sphere in hydrostatic equilibrium with a spherical symmetry, in which the pressure balances gravitational potential, and it assumes virialization, namely almost complete virialization, equilibrium, hydrostatic equilibrium. It results in a profile which is 1 over r to the minus 2, which is precisely what gives you flat rotation curves. And you have to cut it at some point, because otherwise you will get, what you get is a Maxwellian distribution, but it will be infinite, because there is, in this model, there is no boundary, essentially. But you have to say where there is a cutoff. So essentially, you measure, you model the halo with a Maxwellian distribution addressed with respect to the galaxy. So the average velocity is minus the velocity of Earth, or the velocity of the sun, mostly the velocity of the sun. The velocity of Earth is 29 kilometers per second, the orbital velocity, and the velocity of the sun is, I show you, about 220 something, the circular velocity, 230. So it's mostly, and then the escape velocity, which I will show you the data in a moment. So that means that at some point you don't have any more particles, they escape from the galaxy. There should be an annual modulation precisely by what I said before, that actually the velocity of the Earth sums or subtracts, actually a component of it sums or subtracts, with respect to our velocity with respect to the dark matter, or from our point of view, the velocity of the dark matter with respect to us, right? Now, the ecliptic, the orbit of the Earth is at 60 degrees from the galactic plane. So the velocity of the sun, there is a small proper velocity. It's not exactly follow the circular velocity. The sun is moving a little bit outside. Points, the velocity is slightly different, but it's mostly the circular velocity. And then it sums mostly, so the maximal velocity of Earth with respect to the galaxy is in June, at the beginning of June, and then 6 months later should be minimal. And so you expect the kinetic energy changes and the rate therefore should change and so on. You expect a modulation of the rate. Okay, the escape velocity also, again, has been measured. These are measured. Yeah. Well, in velocity, you cut it in the velocity you cut off. You don't, no, this model, is infinite. Yes. Yes, there is no, when 1/r to the minus 2 becomes close to 0 at some point, but no, it's rather, we don't even know exactly, as I said, how big is the halo. We live in our local group. The galaxies are sort of apart. If we would be instead in the center of the Virgo cluster, all the galaxies are so close to each other that actually many of these halos should merge. But for us, it should be separated. And so it is expected, and actually there is some degree of measurement, there is a Keplerian curve. You know, the shape?
The rotation curves are not really flat.
At some point, they should, yeah. When the mass finishes, then the things that are outside from where the bulk of the mass finishes should go as 1/square root of the radius. Well, this is the point that how are you going to measure? You need tracers of light, right? And one of the things that why the error bars are bigger is because you run out of tracers. There are fewer and fewer things that are farther and farther out. So what the last ones are dwarf galaxies that are very far away. No? So I showed approximately where you have a hint of a Keplerian, but with very large error bars. So you can see actually how far it extends. It's maybe it's close to 100 kiloparsecs, but it's not known. Exactly. This is what's called Keplerian behavior. Let us say Kepler is one over. They refer to. They have all these names, and it's 1/square root of the distance. So if you start seeing, that means that the yes, halo finishes. Yeah, but this. Yeah, well, that to the minus 2 is yeah. So it's a very simple model, as I said. It works fantastically well for the relatively simple thing that it is. And of course, I will show you later on all the uncertainties, and then I will advocate for a halo-independent analysis in which actually, instead of assuming, I'm going ahead of myself, but in any case, instead of assuming a model for the halo to get a rate and then to get a limit on cross sections or mass, you use your data, scattering data, to infer the properties of the halo, assuming, you have to assume something, you have to assume your dark matter model. In both cases, you have to assume your dark matter model, but then you would infer the properties. These are complementary. I'm not saying that you should use one or the other, you should use both. And in any case, I like this method. I have been working on trying to develop it since, I don't know, maybe more than 10 years, or for 15 years almost. Okay, doesn't matter. So I hope to be able to tell you something about the halo-independent method, how you get the velocity distribution. Okay. So these are different escape velocities from different things. Here you see it's not extremely well known. It goes somewhere between the late 400s to maybe 600 kilometers per second. And this is as much as you see. Now, this is again, these are measurements. You see, this would be the local at the position of the sun. Instead, this one is trying to measure the whole thing, the global thing. And then you would measure here at the location of the sun, 8.2 kiloparsecs, and then see what you get. But the data are actually have very large error bars and so on. Okay. All right. Now, because of all these uncertainties and because people have to compare data, what you want, if you have two experiments, LC and xenon, you don't want to use entirely different or whatever it is, sensei, whatever you want. You don't want to use entirely different parameters because, of course, then you don't know what is that you obtain experimentally or what is that the assumptions that you made are all different and then you cannot compare. So people got together, before even so, even before this, even before 2021, people were using more or less the same data, 0.3 and so on and so forth. They were using more or less the same model. But then with more and more data, it became necessary to choose maybe updated numbers. And there was then, this was a community effort of people in the direct dark matter community, people from all these different collaborations, they got together, and it's a very nice paper, by the way, 2021, and they picked up these values, and these are recommended values, and I think that people adhere to that. They are reasonable, and then you can compare the goodness of your data or your fits with exactly the same parameters, reasonable parameters, even if they are 0.3 is still 0.3. Doesn't matter because if you want 0.4, you just scale a little bit, right? It doesn't change your. But changing the velocity characteristic, that makes things, that complicates, would complicate actually. So the escape velocity 544, the average galactocentric Earth speed 29, this is 29.8, okay? The solar peculiar velocity is with respect to the circular velocity, and this is here. This was known. Actually, this has been known, of course, with plus minus maybe 1 kilometer per second. Seeing 5 minutes. Thank you. This was known actually, but much better than most of the other numbers because this is the peculiar velocity of the sun. In any case, this is the local standard of rest, 238 in the direction. These coordinates, these are galactic coordinates. So the middle one, this one, is in the direction of motion around the galaxy. This is the choice of parameters. So that's why it's only 0, 238, and 0. Okay. I think I will finish and then with writing the, let me see. Okay, I think I'm going to go with, I'm not going to start with direct dark matter. And we are going to finish with these two transparencies. I think it's a good moment to cut. So here we have then finally the function. This is the function that you get. This is this is a Maxwellian distribution in which you have here all the components, the velocity of the particle with respect to Earth, the velocity of the sun with respect to the galaxy, the velocity of the Earth around the sun. So the velocity with respect to the galaxy would be all of this, of the dark matter particle. And then this is a model with a cutoff. You just cut off. You put a theta function, right? There is another way, and I don't think it makes much of a difference, to make an exponential cutoff. You can smooth out if you want. Who knows? I mean, it's within the uncertainties of this. So it's more of a preference. Then you normalize this integral to 1. For the rate, you normalize, you integrate that to this integral to 1. And with this model, notice that the escape, namely the maximal velocity with respect to Earth that the dark matter particle can have, is not the escape velocity with respect to the galaxies, because you have to sum the velocity of the sun, essentially. So it will be 794 kilometers per second. This is with this advised quantities. And then there is the this is a complicated picture. Maybe it helps, maybe it doesn't. I'm not sure. But it's a different picture, actually, showing that the Earth motion around the sun, this is in galactic coordinates. So here you can see galactic coordinates. And sun, the plane of the ecliptic, the orbit of the Earth around the sun, is at 60 degrees with respect to the plane of the motion of the galaxy. These coordinates in the galaxy are such that the bulk rotation is of the disk is in this plane. The disk of the galaxy is in this plane here. So what I will do is the following. I will comment later on how good the standard halo model is, but for the time being, I will adopt it and then show many things. And at the end, I will talk about different type of uncertainties. And one of these uncertainties, of course, is all this substructure. And besides the bulk properties of the standard halo model, the deviations from hydrodynamic equilibrium. Gaia has seen an enormous amount of different streams. And there could be, there are for sure, there is the debris flows from a structure that has been destroyed already, and it is in different type of, it doesn't show as a definite stream of stars, but it would show in a very non equilibrium distribution of dark matter around Earth. And so all these deviations that would be extremely interesting to measure in the laboratory at the scale of the Earth. Okay, I think we should finish that and then continue with WIMP detection tomorrow. More questions?
I have a very basic one regarding this local measurement of the dark matter energy density. So, do you know if there is any upper bound of like usual density around us? Can I over densities or under densities? So, how should I interpret this mean value you are giving me? That anything that deviates from it by more than the error.
No, there are. Well, you should know actually that the density of all the stuff that is around, dark matter is we are in the very center of the galaxy, right? So it is dominated. It's dominated by baryons. 10 times more baryons than you have dark matter.
That's why I'm confused about this error.
See,
So if you look at the error,
yeah, you have to take into account what remains. I mean, I am not an expert, but these error bars are there.
if you go back to that slide, so go to 40 whatever.
I believe they are under some spherical assumptions. For example, dark stars, right? You can have gigantic overdensities, but then there's nothing, for.
Yeah, that's what I think. So
Yeah, sure.
45.
45. You don't know in.
So you see, like
Ah, sorry. Yes, yes, these error bars, right.
These error bars, I think that they assume something on the distribution.
No, no,
If we measure
distribution. As I said, these are very big distances. I don't think that you can, there is a smoothing. What is the nearest star? There is nothing that can tell you what is in between, but at the distance of the. So all these things are at this made, all these arguments are made at distances that are much larger. It could be that you have much larger than the solar system measurement. So you
have like huge
overdensities or underdensity at the scale of the solar system, we have no idea. Even not only dynamically, but also the simulations. People show simulations here. Simulations usually have particles that, when they are very small, they are thousands of solar masses. So these are the particles that they can, and they have smoothing distances that are, I don't know, a kiloparsec, hundreds of parsecs. So when you say there could be no dark matter at all here, or we could live in an overdensity, actually. There are people are trying to use the dynamics of things that are nearby, planets and so on. It's very difficult because it's dominated by the sun and by the other things, but the dark matter is not dominant. And so sincerely, we do not know. If we want to know how the dark matter is distributed nearby, we will need to measure it. Yes. So it could be. These are huge integration volumes.
So what you mean by local methods
Are distances that are enormous, maybe to the nearest star, parsecs, hundreds of parsecs or something like that, tens of parsecs. I'm not sure what is the smoothing of this, but kiloparsec maybe. The thickness of the order of the thickness of the disk, enormous distances. And so you average on what is inside. But of course, and all the data is like that. We do not know exactly. And until we measure, if we are lucky and we measure dark matter, we are not going to know. Yes.
we know that the Milky Way is like a flat disk, but then we consider the dark matter halo as a sphere.
Yes. Well, no, it's not a sphere. It's a spheroidal. And people are trying. Because dark matter needs to be non-dissipative. Namely, it cannot lose energy as efficiently as the baryonic matter does, because otherwise it would end up in a disk. So that means that most of the dissipative means that it can emit something light and lose energy. This dissipates energy. So baryons, molecules, atoms, I don't know, all this thing that atoms and molecules do at different stages, different things, they emit, they are excited and they emit photons like crazy, or photons of all type of, and they lose energy. And then they fall into the potential well, and but they fall in the potential well conserving angular momentum, because the emission is random and therefore isotropic. And so they lose energy, the particles, but the baryonic particles, without losing angular momentum. So it is like when you do this, I don't know if you do these experiments or making a student rotate. Yeah, so rotate and then again, wait. So you decrease your size, your moment of inertia, omega increases, right? All right, well, this is why. So it has to be, the bulk has to be non-dissipative. A little bit of the dark matter could be dissipative in principle, yes. Would it be dynamically so relevant that would prevent galaxy formation? No. So maybe it could.
You had this citation also about the paper where 10 years ago they were considering if it could have been one of the reasons the dinosaurs.
Oh, yes. Oh, maybe you missed. Yes.
calculating the
Yes, yes, yes. I miss this. There is it. Lisa Randall has this even in a book, I think.
you cited it.
In the dinosaurs, where it was the dinosaurs. Yes, it's double disk dark matter. Here it is. This is the argument. Yes, it has to be non-dissipative. So this is partially interacting, PIDM, but in particular, double disk dark matter will be so dissipative that it would fall in the, and this would be pervasive. If this is a characteristic of the dark matter, any halo that has dark matter means all the halos would form a double disk. In principle, this double disk, they said, could be at inclined, not coincident, but inclined. And then when they were saying that when the solar system traverses this disk, imagine, and it is consistent, the extinction of different species with the period that it could have the sun around the galaxy. And therefore they were saying that maybe it is the type of instabilities that are I'm not advocating for this. I just mention it because I think it's a bit of a crazy idea. It's a lot of a crazy idea, right? So this is what Randall and Rees. But in any case, it seems to be that actually the double, and this is a disk. I mean, double disk coincident with our disk. That would be great because it would enhance the velocities at very low velocities. It would enhance the density. But doesn't seem to be very likely. Okay. Yes.
Part of the explanation you gave about the conventions that were selected for the dark particles, part of that requires a selection of the distribution model. Is that correct?
I don't understand the question.
When the conventions you showed us about the dark matter,
The conventions, yes.
part of selecting that convention, does that require you to select a distribution model of how the dark matter is distributed across the...
No, you have to select a few numbers because otherwise, if you start changing, then you will get not the bands that you get because of other uncertainties in your measurements, etc., but you will get much larger bands because of all the uncertainty in the modeling of your galaxy. That you can do yourself, not so much, because actually the velocity distribution would be complicated. The effect of the velocity distribution in any potential exclusion plot is not easy to have. But so no, you choose a value, reasonable, fixed, and then you compare all your results. If you ever have a signal, that's not what you will do. If you would ever have a signal and you have two different detectors, that's what happened with light WIMPs. That when there were 10 years ago or 2010 or so, there appeared to be 4 different experiments, direct detection experiments, that had a signal that was compatible with light WIMPs, but they were all sort of not coincident, but not coincident if you assume a type of interaction and a type of model. So actually theorists like me started changing all the parameters to see if they could coincide. And actually with some weird things, they could coincide. That's what you would do. So if you have a signal, it's very different than when you don't have a signal, right? That would be an extremely nice problem to have.
Okay, on this
Thank you.
optimistic note, let's go for a small break.